everyone. Welcome to today's lecture on random matrices and universality. Let's first start with some recollection of what we are doing currently. So currently we are in the proof of this theorem 315, or like preparing its proof. And what does it say? Well, we have a beta, and then a vector n, a vector lambda 0, which has n components such that they are ordered. And here now we're in the closure, so there can be coinciding lambdas. Okay, and then we want to prove that there exists a unique strong solution to this system of stochastic differential equations. So we have lambda I, where I runs from 1 up to n for t. Then we have here this drift term. The diffusion term with a constant coefficient here, and independent Brownian motions b1 up to bn. And then here there's a drift term, which is just a function of the lambda i's. And here, so you recall from last time, there's some confining term which avoids that the lambdas become too big. And this here, in some sense, is a repulsive interaction which avoids that the particles, or eigenvalues or particles, as we called them last time, will coincide. So that's what we want to prove here. So the existence and uniqueness. And let me start by recalling what we've already done last week. So the first step in the proof looks as follows. So we take two solutions, lambda I and lambda t and eta t of the system dBm, and we now assume that the lambdas and the etas are strictly ordered, so they are strictly increasing. So there are no coinciding components of the lambda t and eta t for any t. And initially we assume that they are ordered that the initial condition is ordered in the sense that the ith component of lambda is smaller, is at time t equal to 0, is smaller than the eta, than the ith component of eta at 0 for all I. And then the result of this lemma says that then with almost surely for all times they are also ordered in the same way as they used to be. Okay, and last time we've already done the proof, and maybe I should make a small correction here because there was some small mistake in this proof. So correction to the proof lemma 315. So 317. So we had the claim 2, which is still correct, and that said that if I sum up the eta I and the lambda I, then this is smaller than 0 for all times. Okay, so this proof is still correct. And then I don't want to go through the whole proof again, but so what we did there, we defined a t. Define t, which is the sum d of t lambda I eta I. Okay, and then we showed the following, namely that dt is d of 0 e to the minus 1/2 t. Okay, and then from this I wanted to conclude that it's smaller than 0, and then somehow what I did was we somewhat claimed that that from this it follows that dt is smaller than d0, but that's of course wrong. That's wrong because because the d0 is smaller than 0, so that implies actually that the dt is bigger than d0. but it's, of course, the claim is still correct. So but of course the dt is still smaller than 0. Yeah, it's just direct from this relation that the dt is d0 to 1 t. So this here is strictly positive and this here is strictly negative. So that's all what we wanted. So that's okay. So I just wanted to highlight this. I mean, there was so this thing here is of course wrong, but yeah, well, the proof of claim 2 is still completely correct. Okay, so that was this correction, and what we will start with today is a next lemma. Yeah, so we have a second auxiliary lemma for the proof of this theorem. (315), and that reads as follows. So it's lemma 318, I guess. So we take a beta that's positive, and then we take initial value, initial lambda 0, which lies in sigma n. So that means that all its components are strictly increasing, yes. And then we want to prove existence and uniqueness, and that will make our life somewhat easier. So then there is a unique solution. So basically in this setup, we now prove the whole, well, maybe I should say unique strong solution. Lambda t bigger than 0, and that lives. So it's a continuous function of the time with values in the sigma n. To these equations dBm that we saw before. And yeah, the initial condition is this lambda 0. Okay. So maybe you want to take a picture now and record this. And in some sense, this result has somehow the same issue as the other one, namely that there is a regularity, that there is a so I recall that we had this kind of unique existence and uniqueness statements for stochastic differential equations, and here the problem is that we cannot apply them directly because this term here it blows up, and if the eta and if the lambda I and the lambda j come close to each other, then this term here will blow up, so we cannot directly apply these things. And this is similar even if we start with having initially all different components. So if the lambda 0 is in sigma n, because what could happen is that the evolution could drive these lambda I, like to say lambda I and lambda I plus 1 could drive them closer and closer to each other, and then this term would blow up and we would not have control. But actually it turns out that this doesn't, in particular, precisely because we have a plus here, namely that whenever they come to close to each other, then they will repel again. And that's somehow what we have to use in the proof. And this is easier to do if we know already a priori that the initial condition is in the sigma n, so there are no two coinciding particles that are in the same location, and that's what we will use now in this proof. So just to also write this, or at least note this down, what I just said about this issue. So I want to say that the existence and uniqueness results not directly applicable. Yeah, just as I said, because of the singularity 1 over lambda I lambda j these equations. And then just to give a vague idea how we will overcome this issue, it goes in 2 steps. So we first want to regularize this, or use the word cutoff, introduce cutoff. So maybe in the sense that this singularity cannot become too bad, but when the lambda I and the lambda j become too close to each other, then we will cut it off. And that will be parameterized by parameter m. You will see directly that will be the first step to introduce this, how this looks. So that regularizes the singularity. And then in the second step, we have to show that we actually don't need this regularization, because if you choose the m large enough, then the solution will not change almost surely. So that's the second step. Show that this cutoff does not change solution until at time tm. So that will be a stopping time, and that tm goes to infinity. Yeah, well, maybe I should say it almost surely as m goes to infinity. Okay, so we will define a time tm, which says that the solution didn't see the cutoff yet until this time, and then we will actually show that if I choose m large enough, then this will go to this time will go to infinity almost surely, and we will also see that this is that this will be enough to conclude the proof. Okay, and so to start now the actual proof, I first want to introduce a function phi r, which will be used to define this cutoff. So we fix or we take an r, a positive, and then we define this function phi r of x in 2 regimes. So there's an x to the minus 1 if x is at least as big as 1 over r, and otherwise we take r squared times x if the x is very small. Okay, so from that you realize that the phi r of x is at most I think r, yeah. So if the r, yeah, so phi of x is at most r, it's bounded by r from above. So this we will see now how to define the regularized or the cutoff dynamics then. And maybe first I remark that phi of r is uniformly Lipschitz continuous. That was one of these regularity assumptions that we needed on the coefficients. And then I have the following system that we can solve by the existence and uniqueness results. So in particular, this was this theorem 311 that said that the regularized it will be an auxiliary system to solve the final equation. So that will look like this. So I have a lambda IR, the lambda IR dt, the differential of lambda IR should look as follows: square root 2 dBit plus, and then I have the same system as before, except that the singularity, which comes next. So the j different from I, and here we use the phi of r, or the phi r, and then of this difference. Dt. I runs from 1 up to n. Yeah, so maybe you want to take a snapshot now. And this we start at the same initial condition before. And this has a unique solution because these functions here, they satisfy all these conditions that we needed, precisely because this function is uniformly Lipschitz continuous, and it and in particular it's bounded. Okay, or it grows at, yeah. Okay, so maybe let's continue here. So I have to fix the initial condition. And the initial condition lambda 0 is the same as the lambda 0 that we used before, and that has a unique solution. Unique strong solution, and yeah, this I want to denote by lambda RT. Yeah, as before, components have a lower index. Okay. So this we have, and now the idea will be that that this will actually be also a strong solution of the initial system without this regularization, as long as the time is not too big, in the sense that as long as the lambda i's and lambda j's did not get too close to each other. So maybe I should make this as a side remark. So that will now be the main task for the rest of the proof. Note that we should have, it's still an idea, lambda t. So the solution we are looking for should be the same as this regularized solution if the minimum over I different from j, when I compare lambda I r of s minus lambda j r of s. So if this is still bigger than r to the minus 1, then for all s smaller than t, then of course this phi r didn't do anything. So this system actually looks exactly as the system that we actually want to solve. So as the singular system. So in that regime we should have that, and yeah, maybe and that's also how we want to find. That is how we will construct the solution lambda t. Okay, so that was a side remark. So that's maybe an amendment to this idea of the solution that I had here. And And now we want to make this more precise, and to that end I have to introduce some new notation, namely a function f, which lives on the sigma n, so the n vector, so the vectors with n components such that they are strictly increasing. And this is f of x, which is defined, components x1 and xn. And it looks as follows: it's 1 over n, sum I from 1 to n, xi squared minus 1 over n squared, the sum over I and j different from each other, log xi xj. Okay, so that's this function. And then we make a specific choice of our r, and that will be the parameter m that I talked before. So m is now the basic parameter, and r is a function of n and m, and it's defined as follows: it's e to the n squared 4 plus m. And we also define something else, namely the Tm that I already mentioned before. So that looks as follows: it's the infimum over the time t, such that if I test f with the vector lambda r of t, then I want to be bigger than m. Okay, and that should remark that this is a stopping time, as the sense that we introduced it last week. So it's always you can always decide whether this time has already occurred. Sorry, based on the knowledge that you have up to time little t. So you can check whether the time is smaller than t on this in this filtration that we fixed. So note that Tm is a stopping time. With respect to the filtration that we are always using now. Okay, so I hope you took a snapshot here, and then maybe take another one now. And now, what I mentioned before now in sketched here in blue, that will be the first remark now, or the first claim. So for each m positive, we have the following, namely that the minimum of I different from j, and then I compare the components here before, lambda IR, lambda JR at time t. This is bigger or equal to r minus r to the minus 1, and this restricted so we have that this is for all t smaller than big T, and I have a solution of this equation dBm that we want to solve, and this holds on the event when t, so t is the deterministic value now, smaller than the stopping time Tm. Okay, and and then maybe I want to write it a bit differently, because I still want to give this minimum special name. This I want to call 1. So let's I j. Okay, so this is the whole claim that we want to prove now, and for that we need to know something about this little f, and I will actually not go into the details here. I guess this is some trivial arguments with some inequalities and interlocks. So I use the following: when I have a log of x minus y, this is smaller than log of 1 plus x plus the log of 1 plus y. So that's essentially just triangle inequalities. And the second one we use is that x squared minus 2 log of 1 plus x, that this is bigger than minus 4. Okay, so yeah, maybe go up to here. And this we can use for the following properties, namely that the f of x is bigger than minus 4, and 1 over n squared log of xi minus xj, this is smaller than f of x plus 4 for all I different from j and x in sigma n. Okay, so I'm sure if you sit down at home for 5 minutes or so, you will be able to prove all of these statements. So yeah, just first start from those things, and then you will directly get this here. So I don't want to say more about this proof. And yes, so then we can use this to prove the following. So hence we get that lambda I r of t minus lambda j r of t, this is bigger than, so if we use this, I use this relation here, exponential of minus n squared f of lambda r t plus 4. And yeah, by the definition of the stopping time, this here will be bigger than m, but then this whole thing here will be bigger than r to the minus 1. So yeah, and this holds for I different from j. So this proves 1. Yeah, for all t smaller than big T on the event big T smaller than the stopping time. Okay, so I hope this is clear. So that's the definition. It's the definition of the Tm here. So we know that the f of lambda r is lower bounded by m. And then the other thing is the definition of r. Yeah, well, maybe I can add this. So by the definitions of Tm and r. Okay, so if you want, maybe you can take a snapshot now, and then but then it's also quite straightforward to to conclude that the lambda R is a solution. This is just because now on this event, we proved that the cutoff will not have made any difference. So yeah, so we know that the equation is effectively just the same. So moreover, lambda RT is a strong solution of DBM on the event T smaller than Tm. Yeah, as if I apply this phi of R to the lambda IR T minus lambda R, lambda JR T, this is just what we want. By 1. So this proves the claim 1. So the point here is that due to this inequality and then the corresponding inequality 1, so which says that the minimum is bigger than R to the minus 1, the solution actually up to this time Tm does not see the difference or the cutoff here. So that will just not change the solution, because the function phi R here is the same as what we want it to be in the full equation. Okay, and now the second, so I can maybe take another snapshot somewhere here. And then the second claim now will be that this time Tm goes to infinity almost surely when I send the m to infinity. And once we've proved that, we will directly be able to conclude the whole result. So claim 2 is T. Now I have to choose m squared for some technical reason in some sense. That converges to infinity almost surely as m goes to infinity. Okay, and well, that will be essentially an application of Ito's formula, but we will have to compute a bit for this. So let's start with defining two functions. That will make the writing in the rest a bit shorter. So so we will define, well, essentially two n functions, two n functions. They're indexed by I and j, where I runs from 1 to n and j runs over 1, 2. So it's u, I, and j. They live on sigma n and go to R. And they're defined as follows. So ui1 of x is the following sum. It's sum over k, where k is different from I, xi minus xk. That's the thing we already know. And then the second one is the ui2 of x, which is essentially minus the derivative of the first one. So it's 1 over xi xk instant squared. Okay, and then for any so for all these sigma n's. Okay, and then well, then we can rewrite we can use claim 1 to rewrite the the derivative of the lambda IR a bit, the differential. So 2 beta n square root dBit, and now this singular term, we can write it with this function u. So plus 1 over n ui1, and then of lambda r t dt. Yeah, and then I runs from 1 up to n, and this holds on the event t smaller than tm. And yeah, what we want to show now along the argument is that the tm actually goes to infinity, so this event is actually essentially the whole probability, but yeah, the whole probability space. Okay, and yeah, as I already said, we want to use Ito now. So now everything is regular, at least on this event. So by Ito's formula, so that was theorem 3.8. We have the following. So I want to compute now what f of lambda rt looks like. So I have it. I'll just write out the whole formula. df dt. Yeah, maybe I should also have an argument. Lambda rt. That's of course 0. As you remember from the function f, which was not explicitly time dependent, then df dxk to lambda r, d lambda k rt, and then 1/2, and then the quadratic or the second order derivatives, x k x l lambda rt d lambda rk d lambda l r t. Okay, I hope this is, well, okay, this is not really readable. I'll try to make it a bit better. So this is a dxk of lambda rt, and then yeah, dr kt d lambda r l t. Okay, I hope this is better now. Okay, and then yeah, it's a somehow straightforward computation that I now omit mostly the time arguments. K r, this is the coefficient in front of the diffusion term, and then delta k l dt, and the df dt is 0. And moreover, we have the following identities. These you can check. X L of x, this is 2 over n, so 2 over n squared ul1 x. And now because of this delta ik, we only have to compute the second derivative, no mixed second derivatives, but just the second derivative of with respect to xl. So I have df xl squared of x looks as follows: 2 over n plus 2n squared ul2x. And yeah, as I said before, this comes from this derivative formula. So the ul1 xl of x is minus ul2 of x. Okay, so this is some straightforward algebra that you can check, and then and now I have to plug everything into this formula, and then I can simplify it a little bit. Okay, so thus everything looks as follows. So the df lambda rt equal to, now I should remark that here I start dropping the t dependence, or I'm not writing it. Maybe omitting the t dependence from the notation. So then the formula looks as follows. So I have the so I have everything here. If you want to take a snapshot and you forgot about it, then just send me a message in the chat or so, and then I can go to the specific place. So now what we will do, we just plug in these derivatives into this formula up here, and then I end up with the following. And then of course I will also plug in the d lambdas. Okay, so for the first, so this term vanishes, and for the first term here I get the following. I get the sum over L. Somehow I changed K to L. Sorry about that. D lambda R minus 1 over N U L1 lambda R. And then I get the definition of the D lambda K or D lambda L. So it's 2 beta N dBl plus, and then I have the minus lambda L R over 2 plus 1 over N UL1 lambda R dt. So that's the first term, which looks quite complicated. And then I have the second term, which is somewhat a bit simpler. So it's 2 divided by beta n squared. So I have 1, 2 here, 1, 2 there, and 1, 2 here. So only one survives upstairs. And then I have the sum over L, 1 plus 1 over N U L2 lambda R dt. Okay, and then of course we want to combine. Want to combine the dt's and the everything that's db. We will put in a different object. So maybe you want to take a snapshot now. So you haven't done so yet. Okay, so let's go through this slowly. I want to pull out the 1 over n, and then I have a sum over L, and then I want to first collect all of the dt's from the first term here. So this 2 I want to cancel with the 2 here, and put another 2 here. So this will look as follows. I get a minus lambda L R squared. So that's this term with this term. Then I get this this term here with this one. That looks as so it's a plus lambda R over N U L1 lambda R. And then the other one, this is this one and that one. So that's a 2 over N lambda L R U L1 lambda R. And there is a minus 2. So that's the last one. Minus 2 over N squared U L1 lambda r. Okay, that was the first group. Then the second ones I don't change, and then I have to collect the B, the Brownian motion, the drift terms. So that's 1 plus 1 over n UL2 lambda r dt. And then the rest I want to write as a dx. Where the dx looks as follows. It's 2 times square root of 2 square root beta n to the 3/2 sum L from 1 to n r minus 1 over n UL1 lambda r. And now this is with dBl, and then yeah, maybe just to yeah. Okay, I think I want to leave it like this. So that was this computation. So now we have the first step, and I think yes, I guess we can continue for 2 lines, and then we are at a natural place for a break. So what I want to do now, I want to combine. So now I can combine. Well, obviously I can combine this one and that one. But then there's also actually a relation between this here and the U2L, which I want to use next. And there's a relation if I sum over L here, and there is a relation if I take the UL1 and sum over L. And these two identities I want to use now. So maybe you can take a snapshot if you haven't done so. And then I want to do the following. So I give you these two relations that I meant. So we now use the identities they look as follows. So let's start with the, of course I made a mistake here. So here I forgot the square. So this whole guy is squared, right? Because there's a UL here and a UL there. And otherwise the identity of course doesn't work that I want now. So L from, I sum up from 1 to L, from 1 to N, and then I take the UL1 squared, and then this is the same as the sum UL2 of X, and then there's a one for the other term, so that looks XL UL1X, and in fact that turns out to be a constant. So I guess when I tried to explain them before, I just said the wrong thing. So so if I square the UL1s and sum them up, I get the sum over the UL2s. And if I multiply UL1 with XL and sum up over L, then I get a constant. And yeah, I don't want to go into the proofs here as before. The estimates of S for F, they're easy to prove, and in fact they're even, well, they're an identity, so they on this level tend to be easier to do. Okay, and now I want to combine various terms. Namely, I want to start with the term, with this term here. Then I have this term UL squared, UL1 squared, and for this term I can use this identity. And then I have a similar term which comes from this here. And these ones I want to combine first. And yeah, of course, we are still interested in looking df lambda r of t. Okay, so I combine these red things now, and I end up with the following. So I first have let's do this in red, then it's clear where they come from. So it's a 2, 1 minus, I will write down the result and then explain you where this comes from. So lambda 1 to r ul 2 lambda r. So that's the combination of this term here and this term using this identity, right? I guess if you sit down, you will see it. So this here doesn't have a beta, but I can add the beta upstairs and downstairs. It has the same 2 and the same n squared. And there's another 1 over n here and there. So that's n to the 3. And then I have this sum. And then the other term is the other one here, the other red, the one which was underlined, which I underlined in red. This is this term here. Okay, and that's the first dt. And then I can combine some blue terms, namely this one, and well, yeah, the constant term here. And then they look as follows: 1 over n, and I have a 3. I use this identity. There's some n dropping out. 2 beta over n dt. So now I took care of all of the blue terms. And then there is this dx. This I don't want to touch. So this this I can put here plus dx. Okay, and then so that's the form that we will use now for f. So maybe you can take a snapshot, and then I would suggest that we make a break, and yeah, let's maybe continue at 11:20 if there are no questions or comments. And yeah, then that will give us a tool to study this this Tm and prove that this goes to infinity almost surely. And then that's the missing ingredient to show for us the to show that we have a strong solution under this additional assumption that the initial condition lambda of 0 is in the sigma n. So all components are strictly increasing and there are no coinciding indices, and then that will be the first part then. Okay, then see you at 10:20 after the break. Okay, then I would say we can continue. So yeah, what we've done so far was that we derived now an expansion which is, well, more or less explicit for the f lambda of r, and the goal will now be to of course the goal has to be that we have to be able to say something about the probability that this is say smaller than t. Okay, and we basically want to show that this goes to, well, that this is very small when m is large, and the way to do this is that we estimate the expectation. We estimate the expectation of this f of lambda r, and then this here will eventually, after some computation, appear kind of naturally. So so yeah, somehow this is now, well, maybe I should put this aside, and then from this formula for the df lambda, for the df of lambda r, we can get the following. We can write this formula in integral form and then take the expectation, and then it looks as follows: lambda r, and we want to evaluate it at this time where this is so a b is defined as the minimum of a and b, and here the the t is a deterministic time and the tm is the stopping time that we had before. So if I just take the expectation here, then it looks as follows. So I first get this at time 0, right? Just by definition. The integral, then I get something from the blue term, namely I get the expectation of 1 over n 3n minus 1 over 2 plus 2 beta n, and then I integrate, well, that's a constant, and then I integrate with respect to dt. So that's a t minimum tm, and that will actually give us the here we will get the probability in some sense, the that will come later, sorry. And then from the red term we get the following. So and then we get the plus expectation 0 t tm 2 1 minus beta n cube sum L from 1 up to n ul to lambda r minus 1 over n L from 1 up to n lambda L r squared dt. And then there's a expectation tx t minus x of 0, and then yeah, well, this is of course 0. Now let me say something about the individual terms. So this here is, well, the lambda 0 is deterministic, so this here is also deterministic. For the blue term, we have the following, namely the whole coefficient is smaller than 4. And the red term is actually completely negative because, so this part here is positive, this here is also positive. So the ul2 was defined by sums of squares, so that they are positive. But now since the lambda is bigger or equal to 1, this coefficient here is smaller than 0. So that's the place where one uses that beta is bigger than 0. So this whole term here is smaller than 0. So we're only interested in an upper bound on the expectation of f lambda r, as we will see. So what I proved now is that this is smaller than f of lambda r of 0 plus 4 times expectation t m, and then I get the expectation x t m. Okay, and the point now will be that we have to prove that. So what we want to prove now is that this here is also 0, and then we have a somewhat simple form. First I want to call this equation 2, and yeah, as I said, now the point will be to prove that this here is 0, and this we will prove by martingale argument. So we first want to prove that the xt is a martingale. So let's go through this. So now I have the x evaluated at this t minimum tm. So this is a stopping time, so I can use this lemma. I think it was 314. That explains how one can compute an integral with respect to some stopping time, some bounded stopping time. So otherwise, I just plug in the definition of the x. So that was an integral over some sum of Brownian motions. Let's see how this looks. So it's that the little s is smaller than Tm. That's the factor that comes in from the that's the factor that comes in from lemma 314. Then lambda L R of S minus 1 over n sum k equal to 1 m. So I'm just recalling the definition. 1 over, and then I plugged in the choice of well, maybe I just go back to the definition after I finish writing this, and then we see why this is the same. Okay, so where was the definition? Here's the definition of the x. And then I plugged in the definition of the UL L1. And then I end up with this formula here. And now I want to call this coefficient here YL. Okay, so maybe you want to take a snapshot. And now the point will be that this YL is actually bounded because of having the starting time, because of having the stopping time Tm. This here cannot blow up too much, and therefore we will get that this is a martingale by just by the standard properties of the stochastic integral. So that uses again the definition of Tm and 1 in claim 1. We conclude that the YL smaller than C for all L in some constant C that depends on N and R, say. Okay, but that then implies that when I integrate with respect to, well, okay, this is meant as when I integrate, what I want, I need to check now this condition to get that that ensures that something is a martingale, that the stochastic integral is a martingale. So I have to integrate out these coefficients squared, the sum of the coefficients squared. But this is smaller than infinity, so that means that this stopped xtm t bigger than 0 is a martingale. Here I used lemma 3 for the third part. But then we have this homework exercise, which I think we proved last week. That implies that if I take the expectation of xtm, then this is the same as the expectation of x0. So yes, I said this is the, I have here homework 6, exercise 1. But as I indicated before, by definition, the x of 0 is 0. So, so therefore, if I go back to this formula that we proved here in 2, so actually I can also forget about this last term. So what I end up with is now, therefore, 2 yields the following. So I get the expectation of f lambda r t and minimum tm. This is smaller than f at the initial condition plus 4 times T minimum Tm. Okay, so that's what we wanted, and now there's the, or well, that's what we will use now, because now there's a way of finally getting the probability that Tm is smaller than T to get this into the game. Namely, if you stare at it for a second, then you will see that this is the same as I take the expectation of f at lambda r t m plus 4, and then I have the characteristic function that t is bigger than, a little t is bigger than tm. So why is that? Well, if the little t is bigger than tm, then that means that this minimum here has to be tm. But evaluated in the stopping time, this here is m, and we have the plus 4, and then what is left, so this here is a constant, we can pull it out, that gives the coefficient here. And then what is left is the expectation of this characteristic function, but that's exactly this event. So that proves this identity. And then I can use that the f of x is bigger than -4. So that means that this coefficient here is positive. So I can forget about the characteristic function here. So I get an f lambda r t minimum tm plus 4. Okay, and then yeah, maybe. So yeah, hope you remember that that this was in the proof of claim 1. I think I didn't give it a reference. Okay, and now we can use what we proved before. So this I want to use here now. So then this gives me that this is smaller than, what do I have? So I have the f lambda r0 plus 4 tm plus 4. Okay, and then of course this minimum of t and tm I can also estimate. So lambda r plus 1 plus 4t plus 4. Okay, so in total I get that what we wanted. I get an estimate on the tm is smaller than little t, namely it looks like this. It's 4t plus 4 plus f of lambda r of 0 divided by m plus 4. Okay, so this we can already work with. And now we want to use the Borel-Cantelli lemma, and that's where we replace the m by m squared, because we want this to be summable. So now if I take the sum over m in n, the probability tm squared is smaller than t. This is of course then finite, because now I replace this over by m squared. Nothing else depends on m. So this is summable if there's an m squared down here. So by Borel-Cantelli, I get that the probability that tm squared is smaller than t for all m in n, this is 0. And here I somewhat use that the tm's are increasing in m. So well, let's maybe write it like this, as tmt in m or is it's non-increasing, so the sets get at most smaller, and that comes just from the fact that the Tm is smaller than Tm prime when I make the m bigger. Okay, so if I make the m bigger, then the stopping time will also get bigger, and that's why these events are non-increasing. So yeah, I lost the overview. I hope you took enough snapshots. Maybe now is a good other well, maybe one line. So, and now I can take a union bound in M. So that means just a union bound, that the probability that for all little m in M there exists an m in M such that T of m squared is bigger than little m. This is 1, and that's what we wanted to prove in this claim 2, right? Because that now means that, well, that's the same as that this limit this here when m goes to infinity, that the Tm squared when m goes to infinity converges almost surely to infinity. So that's exactly what I wanted to prove there. So now I prove these two claims, and now I can put them together to prove the lemma. And so yeah, sorry, maybe I can take another snapshot here. As I said, if you need this, then if you forgot something, then just ask me. So now we can complete the proof, and it's just a combination of using claim 1 and 2 in the right way. So by claim 1, we know that if I define the lambda t to be lambda r t for t smaller equal than m squared, and yeah, maybe I should remark here that the m here is the r depends on n and m as we defined it before. Then this is a strong solution of this DBM equation, and it also satisfies what we needed, namely that, well, the components are all different, so are strictly increasing. So this is in sigma n. Okay, and now we know that the T m squared goes to infinity as m goes to infinity. So we can consecutively kind of define the m, define the lambda t. Sorry, there was some order is wrong, so should of course be almost surely as the m goes to infinity. That was the claim 2. So from this, combining these two together, we get existence. So if you want to define the lambda t up to some time capital T, then you choose your m such that the Tm squared is bigger than this, and then you get the solution by just using the lambda RT solution for this m. So that's fine. But in the same way, you also get uniqueness. So and yeah, but by uniqueness you get the same thing, or the uniqueness you get essentially from the same argument. So the uniqueness of this solution to the regularized system. So if I introduce this R, then I always have a unique solution. And lambda t for R smaller than Tm squared, for T smaller than Tm squared, and claim 2 imply uniqueness. And that finishes the lemma. Okay, let's go through this last part again. So yeah, if we want to define lambda t for some specific time t, then we just choose the m sufficiently big such that the Tm squared is bigger than t, so we can define the lambda t there, and then patching this together gives them a solution for all positive t's. And by the uniqueness the same. So if you want to have uniqueness up to a certain time, then we can make the m large enough such that Tm squared is bigger than this t, and then we have uniqueness on this whole initial interval, say. But if we have if we would have non-uniqueness, then of course also we would have non-uniqueness on a certain interval. Okay, so that completes the proof of the lemma, and so that means that what we've now proved is that we have proved the following lemma, namely that if we would start from something that's in sigma n, so where, as I already said, we have initially already know that all particle locations are different, so they are strictly increasing, then we find a unique strong solution. And now the point of the remaining proof of lemma 3.15 of theorem 3.15 will be to get rid of this condition, so namely allow for lambda 0 in the sigma n. And the way to do that will be that we approximate the initial condition by something that's in the set sigma n, so so not in its closure, but it's strictly inside sigma, and then we will be able to construct a solution. So then by this lemma we get the solution of this with this approximate initial condition, and then we can send the parameter to 0, and then we get the solution in the strong sense. And for this, to make this precise and to make these to get precise convergence estimate, for this we need a certain other tool which comes from stochastic calculus, which I want to introduce now. And that's what's called quadratic variation. So it's so maybe I put this here as some it's in maybe intermezzo, where I explain briefly what quadratic variation is and how we will use it. And okay.
Can I ask the question about the proof?
Yes.
Why was it named this function f?
Saying so.
Why was it natural to introduce function f?
Well, in some sense, this function f controls. How should I say it? Well, I guess the important property was this here, that that if I control the function f somehow, then I can control how close xi and xj are close to each other. And on the other hand, the f, if we compute the differential, so if you compute this d f of lambda r, then this was sufficiently simple so that we can control it, and we get an upper bound on this, and that then gave us control on the stopping time Tm, right? So of course this is all tailored around this, but the point is that you want to understand the Tm, and that means you have to understand what the f lambda rt does, or what the lambda rt does for large t. And in order to control this, it was easier to first apply the f and then control this. So in some sense, that's a transformation, so that the large t behavior becomes in some sense more explicit and then we could treat this. So does this answer your question? At least I'll give you some idea.
Is there any connection between this function f and the fact that it is a logarithm of the density of distribution of eigenvalues or something?
Yeah, maybe there's a more stronger connection there. I didn't think of it that way. So it could be that in some sense you're yeah, it might be that this in some sense gives you if you think of the lambdas being particles, then that describes something like the energy of the system, and then in that sense it gives you you somehow compute how the energy evolves for large times, and then from this you conclude back that the particles cannot be too close, because otherwise you would get a very large energy.
Yeah, okay.
Is that what you had somewhat had in mind, or?
Yeah, more or less. Yeah, thank you.
Okay. Yes. So let's come back to the. So we now want to extend this statement to the full proof, and yeah, as I said, the tool that we have to use there is quadratic variation, which I want to define as follows. So I think that's definition 319, and so we start with an xt, which is a martingale, as usual with respect to some filtration. And we need two more conditions. So I want that the x0 is 0, almost surely, and the xt squared is a finite second moment for all t bigger than t. Okay, and then this half definition, half theorem, because now I claim that there exists a unique ft adapted non-decreasing process that I want to denote as follows. So it's x and then these angled brackets outside t, and t is bigger than 0. Such that xt squared minus xt is an ft martingale. And yeah, this process is then this quadratic variation. The process x t t is called quadratic variation of xt. Okay, and well, there is maybe also some way of representing it where the quadratic variation aspect of the definition is a bit more apparent, and that's given by the following. So there's a different way of defining it, which well, it's maybe a bit more technical in some sense. But which makes this idea of a variation more apparent. So it looks as follows. So the xt can be obtained as a limit when n goes to infinity of these kind of variations. So I guess if you think of the variation of a function, then that's kind of a definition you would come up with. And now here you take it squared, so it's a quadratic variation. And yeah, maybe just to remark, this convergence holds in probability in the setup of the previous definition. And well, maybe you need some. You might need some more regularity on the process, but yeah, that's the idea. And now, why will this be helpful for us? It will be helpful for us because because by the next inequality that I want to state now, which is the main theorem, why it's useful for us, it states that if I take the supremum over such a martingale up to a certain time, then and then I take the expectation of the supremum, then this will be given by the expectation of the quadratic variation, and that's how we will use it. So we will use quadratic variation through following inequality, and actually we will only use the upper bound, but I want to state both. So that's the Barkholder-Davis-Gundy inequality. So so we have an m in n. It will give us, so in fact we want to compute some moment of the supremum of the martingale, and then we have constants lambda m, small lambda m, and capital lambda m, well, which are of course positive, such that the following holds, such that whenever I take a continuous martingale for any continuous martingale, so m, which has the following conditions. So, well, it just the conditions to make sure that the above definition makes sense. So I need that m0 is 0, and if I take the expectation of mt squared, then this is finite for all t bigger than 0. So if I have such a martingale, then we have the following. So as I said, what we're interested in is the supremum when s runs from 0 up to t. And then I want to look at the ms to the 2m. And I take the expectation of this. So that's in some sense the 2mth moment of the supremum of ms for s from 0 to t. And then this expectation behaves exactly up to these constants like the quadratic variation up to t. And they have to take the quadratic variation, the mth moment. So like this, and then there's the lambda m expectation m t m. Okay, and then maybe here it's best to write it like this. Yeah. Okay. So that's in some sense yes, I said. So you want to understand what the say 2mth moment of the supremum of ms is. And then you can understand this by understanding what the nth moment of the quadratic variation of M is, and then there's some constants, but otherwise it behaves precisely like this. And then of course then you can ask the question, well, this quadratic variation is very implicitly defined, so something has to be a martingale. That's a bit complicated, but in many cases this is easy to compute, and we will do it via the following lemma. So we will the next lemma is a helpful tool to compute quadratic variations. And yeah, I mean, we already have seen many processes that that emerge as a stochastic integral, and this will give us a way to compute quadratic variations of stochastic integrals. So I want to have now, well, let's say L Brownian motions that are independent Brownian motions on R. And then we assume that we have a process, say xt, which is given by the integral of some yi of s db I of s. And then we want to compute the quadratic variation of x. This looks as follows. I have to sum I from 1 up to L. Then I take the yi of s squared, and then I integrate now with respect to ds. Okay, so that's how we will use this. And yeah, in the proof of theorem 3.15, we will have to estimate the supremum of such a martingale, and then we will use this, because the martingale will be of this form, to compute the quadratic variation. And then with this object, we can deal much better, and that will be the way how we use it. And I guess now is a good time to stop. Of course, you can ask any questions or comment if you have some. And then for now, this will be the last tool from stochastic analysis that we will use. Then in the next week, I can complete the proof of theorem 3.15 by combining these results that we had before. So the result where we can compare two solutions that are ordered of the DBM equation, and then we can use this via an approximate via a solution with an approximate initial condition to then get a solution to prove existence and uniqueness for the general setup with the general initial condition. Okay, then I think I stop here, and then see you at 1/4 past in the exercise session.